So essentially, a flow is an asynchronous data stream that sequentially emits values and completes normally or with an exception. How are we going to talk about this for 40 minutes? Well, I had to shorten down the speech, so I got you covered. I'll try to get us all just up with the basics, get us into the context, and then we're going to talk about a few different things. We're going to end with exceptions, which is everyone's favorite topic. Thank you and welcome. I know everyone's eager to get lunch, but we'll flow through this quite quickly. Um, my name is Bob Dahlberg. I've been a developer for over 20 years, so more than half my life, and mainly been focusing on Android. But last year, I actually done Kotlin on the backend side. But in January, I'll be back on the green side on Android again, so looking forward to it. And today we're going to talk about the flow, and more not really from an Android or backend perspective, but more of the flow as a construct, as a system design component. Hopefully you'll learn something and make good decisions on when integrating flows in your specific domain. So essentially, a flow is an asynchronous data stream that sequentially emits values and completes normally or with an exception. So how are we going to talk about this for 40 minutes? Well, I had to shorten down the speech, so I got you covered. I'll try to get us all just up with the basics, get us into the context, and then we're going to talk about a few different things. We're going to end with exceptions, which is everyone's favorite topic. So let's get started with some basics just to get everyone around. So we can create flows in various ways. This is one way of just creating a flow that emits 1, 2, 3. We can have intermediate operators, like on each, map, filter. All these create a new flow and returns that new flow. So we have to operate on a new flow if we want to use the intermediate operator. And then in the end, we have a terminal operator, like collect, single, to list, that actually executes the code of the flow. And then there's a special one that I really like when designing flows. It's on completion. It's also an intermediate operator, so make sure to put it in before you collect. I've done the mistake of having on completion added afterwards, and it doesn't happen, and nothing happens. So it's good to remember. But it always prints. Either if we complete it normally, it just prints what you have, or in this case prints, it executes, or with an exception, so you can see and figure out and have a quick way to understand why your flow didn't work or did work. But usually we write flows like this in a chaining order. But it's good to know that each intermediate operator returns a new flow that we have to operate on. And a common misunderstanding when talking with juniors about flows is that the flow is doing everything. It's the building blocks. We support our logic there, and it helps us collect and aggregate. But there are really two parts. We've got the flow, which is more like the railway. If you think of a train, or like a railway with stations, nothing happens unless you have collectors. And the collectors is more like train. You put them at the railway, and it runs and picks up people at the stations. So to really grasp this and understand that the flow is so little magic, we're hiding the logic, but it's very little magic. So just have a look into the code if you feel like, I don't understand what this does. It's often very easy to grasp. So here I have a bare flow, just emitting 1, 2, 3. And then, that one stopped working. Then I have a flow collector, and instead of using a lambda, I'm actually printing out the entire instantiation of the flow collector and override the only function it has. which is the emit. And this flow collector gets passed on to the flow, and then it runs through the code, and we just call emit. So it's actually the flow collector we're calling. So each time we emit something, it's just a call to the collector. But often we write it something like this, so it's easy to neglect the collector. So what actually happens when, like I said, it's not that much magic with flows, but we have a lot of operators that helps us do things or hide things. As I said, just look into a function like toList and see what it actually does. It can help you design your own flows later on. So at the top we have the toList extension function, and all it does is provide us with a default array list or mutable list if you don't provide one. And then call another extension function, and all it does is collect the flow and adds the items one by one into the list and then returns the list. So no magic, it's just constructs of code. And also when Flow came, there was a lot of discussion with hot and cold, and RxJava was very popular and said to be not as good because it wasn't designed to be cold from the beginning, and flows were. So let's dive into the definitions for cold flows. They execute the same logic every time. So like a railway, it's there. You run the same track all the time you put a train on it. And with a hot flow, it emits values from an active source. It can be the active source itself, or it can have an external active source, but it doesn't really care. It's independent of its collectors. So it emits even if there's no collectors there. These boundaries are about to be erased a bit. More about that later. Let's look into the cold builders. So we've seen this one. We can type our builder a flow of. We can have different types. We can have a list, an as flow, or an int range, or any range as a flow as well. And this is just Kotlin's way of sugaring things. They all boil down to a proper flow. So the simplest flow builder is just called flow. And we can write it as this. So it's not that much to it, but you can make it very useful. Here, for example, I have a fetch flow that just looks into the cache for a URL. Every time it gets collected, it looks to the cache, emits the cache so you can get the result right away. And then if the cache is stale, or if we're going to force fetch it, you can do an actual fetch and then emit the fresh data. We can extend this a lot. This is just a naive first version. We can look at when does the cache expire and delay and continuously update. But it's quite awesome that from a small flow we can actually have this built-in logic. Another cold builder is the channel flow. It looks very similar. So why do we need this one? Well, let's first dig into what the difference is. It's a channel flow, so we know it's a channel. And channels in Kotlin are used to communicate safely between coroutines. So there's something there, and we're sending and receiving on a channel. And instead of emitting, we're sending. So we're using this channel. Let's see why soon, but in Kotlin flows, there'll be rules. And the first rule of flows are context preservation. I'm going to read this one, try to follow. Context preservation in flows means that a flow strictly maintains its own execution context, isolating it from downstream operations. This ensures that transformations and terminal operations run in a predictable manner without leaking or altering execution context to other parts of the flow. I'm exhausted just reading this. Think about it, if you're the first time reading this, you're probably that's just nonsense, it's just buzzwords. And for me, I don't even know this by heart, but I know the gist of it. So let's try to make it more tangible. Let's go back to our flow. And since we're in a suspending, we're used to working with coroutines, we might want to do this. Hey, we can go to another context, we can fetch things, we can do operations, there's no problem. But this will actually throw an error. So we're trying to collect on an empty coroutine context, but the emission happens on the dispatcher IO. So we get some help on this rule that you aren't allowed to switch context within a flow, at least not when emitting. If we take that to an Android example, if we on each we update a text view with the value that's emitted, and we launch it in our view model scope, then we're thinking about it like update is going to be on our main dispatcher, on our main thread, and that's the only place we can update our views. But here we switch the context. So here we actually try to update the view on the dispatcher's IO context. So we're not supposed to leak the context downstream. We can only affect upstreams. That's why this rule is there. What about this code? Hands up if you think this one works. Come on, don't be shy. Yeah, I see a few hands up there. This actually works. The context preservation is, as we saw in the error, the emission happened on the wrong context. This is perfectly fine to do. I wouldn't recommend it, but it is, because we are not emitting inside a different context, so we're preserving the flow's context. But that's why we have other ways of doing things. We can use a flow on, which changes the entire upstream to flow on a new dispatcher. And this way the flow can actually handle it. But also it feels like we're having a hammer, making it a nail problem, and just we're going to force in this. That's why we have the channel flow. And since it was emit or emission that couldn't happen on a new dispatcher, sending is okay, because the channel flow handles the context preservation in the receiving part of the channel. So we can send from different coroutines from wherever, and the channel flow will handle so that we don't switch context for emission. That means we can actually launch coroutines in here. We have a producer scope and we have a channel, and we can do whatever in here. Given that we have a producer scope, we also can await close to do some cleanup if we have long-running tasks, or if we want to cohere to when someone just takes a single item, we might want to cancel our coroutines running in here. So this is really cool function, but beware that this flow right now on the screen will never complete normally, because the await close is suspending. It's waiting for something to tell it to close. So we need to either have the channel that we have implicitly calling close on that one. That will invoke the await close. Or if someone just takes one value or cancels the flow from the outside, then it's going to be invoked. So it's a good practice to have it, because you're listening to what the subscribers or consumers, collectors are wanting. But beware to always close the channel. Let's make it more of a good example. So we have this channel flow. We're reading by line from a file, and we're reading line by line from a buffered reader and sends each line. And then we're done with the entire file. We're going to close the channel. And the await close will clean up everything. So in the happy path, the job or coroutine will already be done, and the reader will already be closed. But it's okay to call them multiple times, because they're idempotent. So you have to look up how you can clean up properly. But also, if someone just wants to read the first two lines, they can do that. And our await close makes sure that we can cancel the coroutine and close the reader so we don't leak any resources. So it's important to be aware of. We have one more call builder, which is the callback flow. Once again, we have the send instead of emit, so we can operate on different threads or dispatchers and contexts. And the callback flow, the name gives it away. It's used to wrap or encapsulate a traditional callback. So here we have a location request, and we build up a location callback that we register when we request location updates. And each time we get a result and callback, we're trying to send, because in most callbacks that are out there that we wanna wrap, they don't have the suspend. So we can't just call send. We need to try send or try send blocking depending on what we want to do. And from that we will get a result, and we can close it on failure or just ignore it, but we can actually reason about, okay, this is failing, so then we might want to close it. And in callback flows, the await close is almost mandatory. I say it's mandatory by heart, but it's not enforced completely. If I remove it, I will get an exception. But if I manage to close the channel before, then I won't get the exception. So the callback flow looks when it finishes, is the channel still active? Then I'm gonna throw an error saying you need to await close. But either way, we should adhere to, if someone closed the flow from outside, we want to clean up and remove our registered listeners. Another big topic when Flow came was, hot building. We need to see our hot builders as well. And in hot, they don't really come as builders, but instead you instantiate one of these, the state flow or the shared flow, and if you want to alter it, mutable state or mutable shared. And as we heard earlier today, the mutable state flow always has a state. So we need an initial state, and every time someone starts collecting, it's going to get the current state, and then every update from that, every distinct update from that. So for example, a player, if you have a music player, we want to keep the state on, switching screens. We want to go back and always have the current state when we have a new screen, a new play button up and running. And we want to listen for the changes. So very suitable for like view models and keeping your state. And for our shared flows, it's more like a radio station broadcasting. You tune in to the radio station and you get events from there and forward. So one would be maybe a ticker that just starts counting. And this code is a bit clunky, and it's how I started using the shared flow. We're actually creating an instance, and then we launch a coroutine to be able to update it properly. So I'm using another way to do it right now. I use a cold flow builder with the exact same logic in it, and then I use the share in instead. So I don't have to keep track of an instance and everything. I just get the flow. And then I have to launch it within a view model or a scope. And then we have some starting strategies. Eagerly just starts the flow directly, and it keeps going forever, or until the body finishes. With this code, it runs forever. We have lazily, which is quite simple. It just doesn't start until the first collector comes, and then it's going to continue forever. And then we have this one that is not really hot. It's absolutely not cold. It's sort of warm, making the flow warm instead of hot. It's while subscribed, because it actually cares about the collectors. When the first one comes, it will start, and then it will continue. It doesn't matter how many collectors, and they all get the same values. But if the last collector stops listening, it's going to stop. And if a new first one comes in, it's going to restart. So that's the difference between while subscribed and the other ones. And that's why I feel like it's not really hot, it's warm. It's up there, but it's not hot. And of course, the state flow also have this state in with the same starting strategies, but you need to provide an initial state as well. Now, another big topic when Flow came was that it handled back pressure in a good way, in a good manner, and it was designed with back pressure in mind. And for flows, back pressure refers to the situation where a flow is or a producer is emitting items faster than a flow collector or consumer can process them. And what we mean about flows handling this gracefully or in a good manner is because we're using coroutines and suspending, and the emit is suspending. Here we produce an item at a rate of every 10 milliseconds, and we collect them in a rate of every 100 milliseconds. So this will actually, the collector will slow down the producer. So it won't get overflooded, it won't miss emissions, but it will actually slow down the producer. And that's how it's gracefully handling it. So each emission here is going to take 110 milliseconds. And that's fine in most cases, but sometimes you don't want to slow down the producer. You want to have accurate producers. Like if you're reading from a sensor, you want to read every 10 milliseconds to always have the freshest data. But if you have a collector that is doing a lot of stuff, it can slow down your flow. What we have then, we can add a buffer to it. And the buffer is good when your collector is slow once in a while. So we can buffer up, and then the collector gets up to speed and consumes everything. But if collecting is always slower, then we're just going to delay the slowing down of the producer by the size of the buffer. So there is also strategies to the buffer. And the default one is suspending, so it's just going to suspend when they hit the roof of the buffer. But we also have drop latest or drop oldest. And here I changed to a buffer size of 1 and dropping the oldest. So every time we emit, we're going to remove if we have a buffer already and put the new one up there. And this one is actually named conflating. And of course, Kotlin has sugaring for that. So we can conflate. And this is sort of like how the state flow works as well. It's conflating. Now we're never going to slow this flow down because it's going to keep emitting and just keeping the latest in the buffer if someone starts being slow on the collecting side. We can also, maybe we don't control the flow and we want to do it later on. There's a new kind of neat feature that is sampling the emission, where we can set a window of, here I set it to 10 seconds, and we're only going to care about the last emission during those 10 seconds. And we're going to operate on that one. So it's kind of cool if you're just interested. You don't want to drain your UI with some flow that kicks in every minute, like listening to a touch or an animation. You just want pieces of it. You can use this sampling. And now what you all came for, exception handling. I'm not going to go in too much into cancellation. We had a great talk about it earlier. But it's good to be aware that cancellation in flows works as in coroutines if the flow are cancelable. And most of them are, but for performance reasons, the int range as flow is not cancelable. So this code actually runs for 5 seconds and emits everything from 1 to 10, or prints it, yeah. So if we want to make this cancelable, we need to add a function to it. And again, there's no magic in the flow. So if you go into and look at this function, it's only calling on each assure active. And that's all the magic. But we like sugaring in Kotlin, so it's nice. It's descriptive. Enough about canceling. Let's talk about exceptions that we cause. So remember this code? We have our flow, we're emitting things, and we're fetching from the network. What if we want to be a bit safer and just have a try catch, or as I want to use the run catching? We're not allowed to do this because there is one more rule for flows, and it's exception transparency. So essentially, we're not allowed to emit inside a try catch block from a flow, because if we follow this, it guarantees that collectors throwing an exception can always catch it using. So the collector should be able to catch the errors. Let's make it more tangible as well. But first, there is a way to catch errors from flows. We can have the catch function. The problem is it catches everything. So maybe you want to type and rethrow the exceptions that we don't want to handle. But if we strip this function down to just have the fetch and emit, and if the fetching fails, we want to catch it and we're going to have a fallback. It's perfectly fine logic to have a fallback, but what if our collector is a parser that also can throw an error if the JSON or payload is malformed? So in the happy path, it just fetches and emits. In the logical happy path, the fetching throws an error, we catch it, and we provide a fallback. But if the parser throws an error or anything in the collect, we're also going to catch it inside our flow, because the emit is just calling a function. So we're actually swallowing someone else's exception, and that's why we have this exception transparency principle. It's not enforced by compilers, but it is a rule of flows. So we need to be wary that we shouldn't swallow and handle someone else's errors or exceptions. And the last thing I want to mention about exception handling is this on completion that we saw earlier, that I used to debug everything with flows, because it's like a finally with superpowers. So if we add it to a flow, we're sure it's always gonna execute. And if there's an error, it's gonna show there or provide the error so we can reason about it and look at it. And if it's not, if it's completed normally, we will get a null. And this will output 1.4, and then we're gonna get the on completion, because it's actually before the catch block. So then it's going to print before, saying we got the error, and then we're going to catch it later in the flow. But if we move the check into the collector instead, and we don't catch anything, we're still going to get the error in the on completion. This is where the superpower comes in. It's actually going to get the errors even from the collect, so the entire flow. But this one is going to throw an uncut exception because we're not catching it in the collect. So we need to always provide a way to catch the errors from everywhere. And this is also one way of ensuring exception transparency, that we're able to do this. We're able to run the flow inside of a try-catch block. And once more, it's the emit that can't be run inside of a try-catch. So if you have a channel flow and you send, you can do that inside of a try-catch block. And that's actually all I had. Thank you.